Hi guys, Mrs. Rossi here. Today we're going to be talking about the atom. We're going to be talking about some subatomic particles, some ions, some isotopes. So you need to follow along with your note sheet and fill it in. Remember, you can pause, rewind, or stop this video at any time if you need to go back and get info that I talk about. So we should already know from all of our atomic theory talk that atoms are made up of smaller things. Those smaller things are called subatomic particles, and our most basic ones include electrons, protons, and neutrons. Here we have a chart that includes the location, mass, and charges of those subatomic particles. We have protons located in the nucleus of an atom with a mass of about 1 AMU, and each proton has a positive 1 charge. Neutrons are also located in the nucleus. They also have a mass of about 1 AMU, and they don't have a charge. And then we have our electrons. They're located in the electron cloud, so outside of the nucleus, and they have a mass that's so small that we say they have a mass of 0 AMUs. Each electron you have carries a negative 1 charge. And AMU is a special term when it comes to atoms that we use to talk about, and it stands for atomic mass unit. The masses of these subatomic particles are so small that they came up with this unit instead, so that you weren't using such small numbers in scientific notation when we were referencing their masses. On the periodic table, and when you look at little element squares on there, you're going to see something known as the atomic number. The atomic number of an element is how many protons that element has in its nucleus. This is what elements are identified by, and you can also use this number to help predict some of the properties of the elements. So the atomic number is usually located on the top of the element square box. You can see on the examples on your note sheet that it's in the upper left-hand corner, and that represents how many electrons that neon, carbon, gallium, and nitrogen have. This also can be used to identify the number of electrons that these atoms have when they're neutral. On the periodic table, we always assume that elements are in their neutral state. APE is a fun way to remember what atomic number represents, the number of protons and the number of electrons if the atom's neutral. So it's a fun memory clue for you. Here are a couple other ways that atomic numbers can be represented. Here we see it's on the top right. Here it's centered on the top. And on this one, it's called isotope notation. The atomic number is actually on the bottom. Mass number of an atom is the sum of the protons and neutrons in the nucleus. Remember, protons and neutrons are the things that have mass. So the mass number is the sum of those, and it also is your total of particles that are in your nucleus. Now we have 8 to remember that atomic number is the number of protons and electrons in neutral atoms, and then man can be used to help us figure out how many neutrons make up an atom. So if you take your mass number and subtract the atomic number, you wind up with the number of neutrons. Usually what we see on the periodic table and what you have on your note sheet is something called the atomic mass. The atomic mass is very similar to the mass number, but it's not exactly the same thing. Your atomic mass is the weighted average of all the naturally occurring isotopes that exist for that atom. And for that reason, to get the mass number, we typically just round to the nearest whole number. So if you have a decimal that in the case of neon, is 20.18, you'll just round down to 20. And for carbon, since it's 12.0111, you're going to round down to 12. In the case of gallium, you have 69.7, you would round that up to 70. So on the periodic table, take your atomic mass, round it to the nearest whole number, and you'll get the mass number. Here are a couple more examples. We can see atomic mass is up here, and then over here, this would be our mass number on titanium. Here's our atomic number down here, and then we have our mass number on magnesium. Here for lithium, we have our atomic number on the bottom, and then the atomic mass rounded is 7 up top here. Up next, we have ions. 8 man, our atomic number equals number of protons equals number of electrons, only holds true if your atom is electrically neutral. So that means you have the same number of electrons and protons. Remember, protons have a positive charge for each one that you have, and electrons have a negative charge for each one that you have. So if you have a different number of protons and electrons in an atom, overall that atom is going to have a charge. If you lose electrons, you're going to have more protons than electrons. So overall, your atom will become positively charged. If you gain electrons, you're gaining negative charges. So more negative charges than positive charges, overall your ion's going to have a negative charge. The special name for an atom or group of atoms with a positive charge is cation. So when atoms give up electrons, an electron or electrons from the valence shell, its outermost shell, it overall has a positive charge. So let's take a look at lithium. Here we see that there are 3 protons in the nucleus, and then we start off with 3 electrons in the electron cloud. One of these electrons in the outermost shell is lost, leaving us with 3 protons in the nucleus still, but only 2 negative electrons on the outside. Overall, since lithium lost 1 electron, it has a positive 1 charge. Here you see that it's just a plus sign, and then the 1 we can just assume. If you would like to also write the 1 here, that would also be correct. A fun memory clue for this is that cations are positive. Think cat, pause, positive. I also like to say that the T kind of looks like a lowercase t, kind of looks like a plus sign, and that's how you can remember cations are positive as well. Here are a couple more examples. Sodium also loses 1 electron from its valence shell here, so overall it winds up when it's a sodium cation with a plus 1 charge. Magnesium, on the other hand, loses both of these electrons from its valence shell, so overall, since it lost 2, you're down to only 10 electrons out here, but 12 protons with positive charges on the inside, so magnesium cation is a magnesium plus 2 cation. Notice how the charge tells you how many electrons were lost in this case. An anion is any atom or group of atoms with an overall negative charge, and this happens when those negative electrons are taken into the outermost shell of atoms. So here we have fluorine that's starting off with 9 protons in the nucleus and then 9 electrons on the outside. We know that 8 total electrons can fit on the outside, so when that 8th electron comes to fill in that empty spot, we have a total of 10 electrons on the inner and outer shell, and 9 positive charges, 10 negative charges, and overall negative 1 charge on this fluorine anion. Here are a couple more examples. We have chlorine that starts off with 17 protons and 17 electrons. When that 18th electron comes in, it means we have 17 positive charges, 18 negative charges. So overall, we have a chlorine minus 1 anion. And here we have our oxygen atom starting off with 8 protons and 8 electrons. But when those 2 empty spaces on that valence shell are filled, 2 more negative charges coming in, giving us an overall negative 2 oxygen anion. Determining whether if an atom will become an anion or a cation depends on how many electrons are in the valence shell. We know that in this first shell, closest to the nucleus, we can fit a maximum of 2 electrons. In all the other shells on the outside, we're going to be able to fit up to 8 electrons. In the outermost shell, if there are 4 or less valence electrons, and those are outermost shell electrons, it is likely that that atom will become a cation. So it's going to give up those electrons if it has 4 or less. If an atom has 4 or more electrons in its valence shell, it's going to take in electrons and become an anion. So let's take a look at this atom. We have 3 protons in the nucleus and then 3 total electrons, but only 1 in the valence shell. Since 1 is less than 4, it'd be likely that this was going to give up this electron and become a cation. In this case, we have 9 protons and we have 9 electrons total right now, but we have 1, 2, 3, 4, 5, 6, 7 in our valence shell. Since 7 is greater than 4, it is likely that 1 more electron would join this valence shell to fill it with 8 electrons and it would become an anion. Another thing that can happen to atoms, and this is usually naturally occurring, is that atoms can also become isotopes. Atoms that have the same number of protons but different number of neutrons are called isotopes. Since the number of neutrons are different, the mass of the atom is also different, changing its mass number. Remember, the atomic number is your number of protons, and it identifies the atom, so that's never going to change. Your atomic mass is the sum of the protons and neutrons that are in there, so that can change and not change the identity of the atom. So here we have our carbon isotopes. We have carbon-12, carbon-13, and carbon-14. Notice that the element dash and its mass lets you know that it's an isotope. This is also the isotope notation. Your atomic number is always on the bottom, and then that mass number, or in this case, they're labeling it atomic mass, is on the top. Isotopes are chemically similar to each other because they still have the same number of protons and electrons. So because they still have the same number of protons and they still have the same number of electrons in their valence shells, they behave in similar ways. Their masses are different, which sometimes cause slight differences, but overall, they're really not that different from each other. Here, watch this little video on isotopes.
All atoms of a particular element have the same atomic number. This means that they all have the same number of protons. But sometimes you can find heavy atoms of a particular element. These atoms have a higher mass number. The mass number is equal to the number of protons plus the number of neutrons. We can ignore the electrons as their mass is so tiny. If the number of protons always stays the same in a particular element, and we are ignoring the mass of electrons, it must mean the number of neutrons is causing the difference in mass. Atoms of the same element with a different mass number are known as isotopes. They are defined as atoms of an element which have the same number of protons but a different number of neutrons. If we look at carbon and nitrogen, are they isotopes? They have different mass numbers. They also have a different number of protons. Therefore, they are not isotopes. They are completely different elements. Different isotopes of elements do not have separate positions on the periodic table. They occupy the same spot because they have the same number of protons. What about carbon-12 and carbon-14? Both carbon-12 and carbon-14 have the same atomic number, which means they have the same number of protons, but they have different masses. Carbon-12 has a mass of 12 and 6 protons. Remember, mass number equals protons plus neutrons. So we can rearrange this formula to give us neutrons equals mass number minus protons. 12 minus 6 equals 6. Therefore, it has 6 neutrons. Carbon-14 has a mass of 14, but it still only has 6 protons. Mass number equals protons plus neutrons. Rearrange. Neutrons equals mass number minus protons. 14 minus 6 equals 8. Therefore, carbon-14 has 8 neutrons. Carbon-12 and carbon-14 are not the only examples of isotopes. There are many more, such as hydrogen, deuterium, tritium, and chlorine-35 and chlorine-37. Isotopes only differ in their number of neutrons and their mass. Their chemical properties are exactly the same because neutrons have no effect on an element's chemical behavior. This is controlled by electrons, which we will discuss in another video. So isotopes are atoms of the same element with the same number of protons but a different number of neutrons. They have different masses, but their chemical properties are exactly the same.
All right, so hopefully you got a couple of examples of isotopes from there. And now we're going to go into how they actually come up with those atomic mass numbers. So we already talked a little bit about atomic mass. The atomic mass is the weighted average mass of the atoms of naturally occurring samples of the element. So here's our first example. We have copper. Copper 63 and copper 65. Remember, these are referring to the masses of copper, and we know that they have a different number of neutrons. Given the atomic mass of copper on the periodic table is 63.546 AMU, which of the copper isotopes is the most abundant? Knowing that it's a weighted average, we can assume that copper 63 is way more abundant than copper 65 because the weighted average is way closer to 63. All right, so here's how we actually do it. We have an element X, and it has two natural isotopes. The isotope with a mass of 10.012 AMU has a relative abundance of 19.91%. The isotope with a mass of 11.009 has a relative abundance of 80.09%. Now we want to calculate the atomic mass of this element and figure out what element it actually is. So we're going to find the mass of each isotope that contributes to the weighted average. We do that by taking each of the elements that we know, the information they give us, taking the percent out of the percent, so you can do that just by dividing by 100 and multiplying by it. So the 10.012 AMUs times the percent, but it's out of percent, and remember you get that by dividing by 100, equals 1.993 AMU. The second isotope is the 11.009 AMU isotope, and we also multiply it by its percent. Take it out of the percent by dividing by 100, so that's how we got the 0.8009, and we get 8.817 AMU. Then you're going to take both of these numbers and add them up. If we had more isotopes of it, we would be adding them up as well. So we have 1.993 AMU plus 8.817 AMU to give us 10.8 AMU. Then you're going to look at the periodic table and see what element has an atomic mass that is really close to this. So you're going to look at the bottom numbers on your periodic table, and you should see that boron is 10.8 AMUs. So this element is boron. Sometimes in this example, they give you what element you're dealing with and ask you to calculate the atomic mass. So now we have helium with two natural isotopes. One isotope has a mass of 3.0160 AMU and a relative abundance of 0.0001%. The isotope with a mass of 4.0026 has a relative abundance of 99.9999%. So hopefully it makes sense when you look at the periodic table and see that helium has an atomic mass, an atomic number of 4, because most of the heliums in this universe have 2 neutrons and 2 protons to give them the mass of 4. But some heliums do only have 3 total particles in the nucleus, but 2 protons, 1 neutron to have that mass of 3. So the first step, just like we did in the last time, was to find the mass that each isotope contributes to the weighted average. And we do that by taking the mass given and then multiplying it by the percent given. So here's our helium-3. So our mass given multiplied by our percent divided by 100, our mass given multiplied by our percent divided by 100 to get it out of the percent, and then we add them up and we see where that number on the bottom of the periodic table actually comes from. Why don't you try this next one on your own? We have copper 63 and copper 65, just like we talked about before. It makes sense that this one's a little bit more abundant, but now you're actually going to see where that number on the periodic table comes from. Did you get the same answer? Hopefully you did. Check your work with what's on the screen. All right, and here's our last practice problem. This one, iodine has iodine 127, iodine 126, and iodine 128, so 3 different isotopes. You're going to do this the same exact way. You're going to set up your problem with each isotope and do its weighted average. Remember to divide those percents by 100. Then you'll add them up to get your final answer. Hopefully you got the same thing. And moving on to our last step, reflect on what we talked about today, what happened to our neutral atoms, and fill in each of the boxes on your paper.